the exponential function. So we're going to start by reviewing the concept of exponential functions, which is something that you have come across previously. You have come across functions of the form y equals a to the power of x. So that means the unknown, the variable, is in the power. And we've got a few examples plotted on the axes below. We have the red graph, which is y equals 2 to the power of x, and y equals 3 to the power of x. And there are some properties of these functions that you have seen previously. These particular functions will cross the y-axis at 1 if they're of the form y equals a to the power of x, because of course if x is equal to 0, then y is equal to a to the power of 0, which is equal to 1. So you have a y-intercept there at 0, 1. As x approaches infinity, y will also approach infinity. And that's partly the definition behind the idea of exponentials. If you have 2 to the power of 3, that's only equal to 8. But if you work out 2 to the power of 10, that's equal to 1024. So the difference in the x values goes from 3 to 10, which is a very small difference, but the difference in the y values goes from 8 to 1024, and we sometimes refer to this as exponential growth. And you can see that as the x values get larger and larger, the graphs increase like this, getting steeper and steeper. As x approaches negative infinity, y approaches 0, and you can see that in this region of the graph over here. Now, because of the limitations of the graphing software, it looks like these graphs have touched the x-axis. They haven't. In fact, the x-axis is indeed an asymptote for these exponential curves, or the curves are asymptotic to the x-axis. So in reality, when we sketch them, we should show them approaching the x-axis, but not actually crossing it. So for instance, if I was sketching an exponential function, I would draw it like this. So you can see that it's approaching the x-axis, but not actually touching or crossing the x-axis. So the x-axis is an asymptote. Now, why does y approach 0 as x approaches negative infinity? Well, let's think about the function y equals a to the power of x, and let's imagine x is equal to negative 100. Y would then be equal to a to the power of negative 100, which is 1 over a to the power of 100, and of course a to the power of 100 is going to be a very large number. 1 divided by a very large number will give you a very small result, and results that will become closer and closer to 0 as that x value becomes more and more negative. Now, as we could see, the graphs of y equals 2 to the power of x and y equals 3 to the power of x have different gradients, which depend on the value of a. There is a particular value of a for which, at any point on the exponential curve, the y-coordinate and the gradient of the function will take the same value. Now, you can experiment with this on your graphical calculator. You can use the autograph software to explore this. And what we have below is the graph of y equals 2 to the power of x. Now, this is drawn in red. So the red graph is y equals 2 to the power of x. And using the autograph software, I've plotted the gradient function, so the derivative for this particular exponential function. Now, as we can see, they're not a perfect match. So the gradient and the y-coordinate do not take the same value for this particular exponential function. So I've now sketched the graph of y equals 3 to the power of x. You can see it in red. And I've also used autograph to draw the graph of dy by dx for this particular function. So For every x value, we calculate the gradient and we plot the gradient as the y-coordinate. Now there's a much closer match here, but it's still not perfect. So there must be a value of a that is in between 2 and 3, for which at any point on the curve, the y-coordinate and the gradient are equal. And we can use autograph and some trial and improvement to investigate values of a between 2 and 3 in the function y equals a to the power of x to find out which one will give us a match between the y-coordinate and the gradient. And here it is below. For the value of a used, there is a perfect match between the function and the gradient function if a is equal to this value here, 2.7182 ... Now, this is something we call an irrational number. You've come across other irrational numbers before, for example, the square root of 2, pi. Now, a certain number of some irrational numbers are given particularly special status because of mathematical properties they have. Pi is one such example, and this number is another example. It's denoted by the letter e. So our value of a here, this number here, we actually call e. So e is equal to 2.7182 ... So this function, y equals a to the x, we can write as y equals e to the x, where e is this irrational number 2.7182. And you can see, plotted on the graph here, you can see the red curve just underneath, this is y equals e to the x. The blue graph that's superimposed on top of that is the graph of the gradient function, and it is a perfect match. So the function y equals e to the x has a gradient function which is equal to the y value, so it's also equal to e to the x. Now this is a property you will explore in much more detail in year 13. You will learn how to differentiate e to the x from first principles, and you will do lots more differentiation using functions that involve e to the x. This function is called the exponential function. So whereas functions of the format y equals a to the power x are in general called exponential functions, this function here is particularly special and it's referred to as the exponential function. And we need to know that the function differentiates to itself. So if you differentiate e to the x, you get e to the x. Now, exponential functions will obey the typical laws of indices. So let's have a look at some properties. If we have e to the power of x and we multiply that by e to the power of y, now the base here in both examples is the same. It's e, and we have to remember that e is just a number, 2.718, etc. It's an irrational number, so a special type of number, but nonetheless it is still just a number and will behave like other numbers. So e to the power of x multiplied by e to the power of y will give us e to the power of x add y, adding our indices together. In the same way, if we have e to the power of x divided by e to the power of y, again, the bases are the same. So this will give us a result of e to the x take away y. If we have e to the power of x raised to the power of y, this is equal to e to the xy, or if we like, e to the yx. E to the power of 0 is equal to 1, and e to the power of 1 is equal to e, or 2.718. If powers are negative or fractional, they work in the same way as well. For instance, e to the power of a half would simply be the square root of e. E to the power of negative 1 would simply equal 1 over e. E to the power of negative 2 would equal 1 over e squared. So these are all the laws of indices which we have seen before. And e will obey these in exactly the same way as any other number. So what can we do with our exponential function? Well, one thing that we can do is explore some transformations of this. So I'm going to define f of x as e to the power of x, and you're going to work out what the effect of each of these transformations is. In each case, you need to write down the transformation in words using the correct mathematical terminology and sketch the graph. You can use your graphical calculator to check whether you have sketched each transformed graph correctly. Now, in each case, you need to make sure it's clear as to what the asymptote is and what its equation is. So sketch the asymptote clearly and make sure you've labelled it with its equation. The answers will come up shortly, so make sure you pause and do this work yourself first of all. So the first question, y equals e to the x minus 2. We could rewrite this as y equals f of x minus 2, and we see it's a translation with vector 0, negative 2, and the graph shifts down to units. Now that means the asymptote, which was the x-axis, also moves down to units, so the asymptote becomes the line y equals negative 2. Be careful with your sketching. Autograph always makes it appear as though the graph has reached the asymptote, but you must show your curve approaching the asymptote and not actually crossing or intersecting it. So example number 2, y equals e to the x plus 1. This is a translation with a vector negative 1, 0. Again, it may help to write this as f of brackets x plus 1 because it's the x plus 1 that is in the power here. Remember, f of x is equal to e to the x, so f of x plus 1 is e to the x plus 1. Now the graph is shifting 1 unit to the left, so the asymptote doesn't move. It's a horizontal shift, so the asymptote is still the x-axis, or the line y equals 0. Now what has changed is the y-intercept is no longer 0, 1. If we take this function here and we allow x to equal 0, then y would become e to the power of 1, or simply e. So this point here has coordinate 0, e. And you can see, of course, e has a value of 2.718, so the y-intercept is just below 3. Question number 3, y equals 2e to the x, also written as 2f of x. This is a stretch parallel to the y-axis with a scale factor of 2, and we can see that the y-intercept is no longer 0, 1, it's 0, 2. Remember, in a y-stretch, the x-coordinates stay the same, but the y-coordinates multiply by the scale factor, which in this case is 2. Because the graph has not performed any vertical shifting, the asymptote stays where it is at y equals 0. Question number 4, we have y equals e to the 3x, which is f of 3x. So this is a stretch parallel to the x-axis with a scale factor of 3. So the x-coordinates will all multiply by the scale factor of a third. The y-coordinates will all stay the same. So we can see that the y-intercept remains at 0, 1, and the asymptote hasn't changed as well. So our asymptote remains y equals 0. Number 5, y equals negative e to the x, or negative f of x. This is a reflection in the x-axis. So the y-intercept, which previously was 0, 1, becomes 0, negative 1. The x-axis remains the asymptote, and the graph is reflected in this as a mirror. Question number 6, y equals e to the power of negative x. So this is f of negative x, and this is a reflection in the y-axis. The y-intercept remains the same at 0, 1. It's an invariant point, and y equals 0 is still the asymptote. Number 6, y equals 3 minus e to the x, which it can be easier to work out what's happened here by rewriting it as y equals negative e to the x plus 3. which is negative f of x plus 3. So this is a combined transformation, and it is a combined transformation in which the order of the steps matters. The first part of this is the negative f of x, which tells us that we have a reflection in the x-axis, which of course will affect the y-coordinates. The next part of this is this plus 3, which tells us we have a translation with a vector 0, 3, which also affects our y-coordinates. So there are two stages to this transformation. Now, if we remember, the original function y equals e to the x looks like this. If we then perform the reflection in the x-axis, it will look like this. So here is our graph of y equals e to the negative x, or a sketch of it. And then the last stage is to translate this by 3 units vertically. Now, this point here, of course, is 0, 1, which reflects to become the point 0, negative 1. And if we shift that up by 3 units, it becomes 1 unit, 2 units, 3 units. So that's 0, 1, 2. So it becomes 0, 2 if we move it up by 3 units. So we can see there's our new y-intercept. And of course, the graph retains its shape, but it is translated upwards like that. And here we have the final sketch, like so. Now, what happens to the asymptote? To begin with, the x-axis is the asymptote. It's still the asymptote after the reflection, but when the graph is translated up by 3 units, the asymptote is also translated up by 3 units. So it becomes the line y equals 3. Now, we briefly referenced the concept of exponential growth earlier on. And an example of an exponential growth would be, for instance, if we look at the very simple function y equals 2 to the power of x. If x is equal to 1, then y is equal to 2. If x is equal to 2, y is equal to 4. If x is equal to 3, then y is equal to 8. Now, we start to see very, very rapid growth. So from here to here, our x value multiplies by 3, but our y value multiplies by 4. If x becomes 10, y is equal to 2 to the power of 10, which is 1024. So our x value has multiplied by 10, but our y value has multiplied by 512. So exponential growth refers to this type of growth where things increase very, very rapidly. And we're going to have a look at an example of a problem involving this concept of exponential growth. So the number of bacteria, which is denoted by the letter n, in a culture grows exponentially, and we can see the use of the exponential function here according to this formula. Now, the letter t here refers to time in days after the start of our experiment. Let's have a look at what we can calculate with this. Part A, how many bacteria are present at the start of the experiment? So at the start of the experiment, this is where time equals 0. So n would then equal 25 plus 5e to the power of 0, which gives an answer of 30. Part B, what is the number of bacteria present after 7 weeks? So after 7 weeks, well, we need to convert that into days. So that is 7 multiplied by 7, or 49 days. And then we can substitute this in for our value of t. So this is n equals 25 plus 5e to the 0.4 multiplied by 49. And we can input that into our calculator. And as you will see when you do this, the answer is absolutely massive. So we have an answer of 1,626,079,806. Now this makes sense because we know bacteria multiplies very, very quickly, very, very rapidly. So after 7 weeks, when we started with 30 bacteria, we've now ended up with 1 billion bacteria. And that is exponential growth. So find the rate at which the bacteria are growing after 3 weeks. So again, 3 weeks is 21 days. We must input that correctly later on. Now, the rate at which the bacteria are growing means that we need to differentiate. We need to find dn by dt. So this requires a little bit of extra knowledge, borrowing this from the work that you will go on to do in year 13. We know that if y equals e to the power of x, then dy by dx is equal to e to the power of x. Now, if we introduce some constants, so let's say y equals k, which is a constant, so it will essentially represent some numerical value, e to the power of, let's say, ax, and let's make it very, very clear that these letters represent numerical values, so they are constants. If we differentiate, then the derivative would be equal to ka e to the power of ax. And you will learn much more about this in year 13 when you study exponential differentiation in detail. So for the moment, we're just going to borrow this fact that if y equals ke to the ax, then dy by dx is equal to ka e to the ax, and we'll use this to help us answer the question. So the rate of which the bacteria are growing is dn by dt, it's the derivative with respect to time. 25 differentiates to give us 0. Then differentiating this part here, we have 5 multiplied by 0.4 e to the power of 0.4t, which simplifies to 2e to the 0.4t. We know that t is equal to 21 days across 3 weeks, so dn by dt is then equal to 2e to the 0.4 multiplied by 21, which works out to be a value of 8,894.133, etc. So 8894 to the nearest whole number of bacteria. Now the last part asks us to sketch the graph of n against t, and you can simply do this on your graphical calculator and then note any key points, but you may want to also think about the transformations that are occurring here. We have a stretch in the x direction. We have a stretch in the y direction, and then we have a vertical translation. So if we were to say that f of t was equal to e to the power of t, then what we have here is n, which is 25 plus 5e to the 0.4t, or 25 plus 5f of 0.4t. So we have an x stretch with a scale factor of 1 over 0.4, which is equal to 2.5. We have a y stretch with a scale factor of 5, and then we have a translation, which must come after the y stretch because they both affect the y coordinates, of 0.25. See if you can sketch these and then check on your graphical calculator. So you can see the first sketch is of n equals e to the power of t. If we then stretch in the x direction with a scale factor of 2.5, the x coordinates will all multiply by 2.5, the y coordinates will still stay the same, so 0, 1 will not change, but the graph will stretch out a lot like this, so this will still remain at 0, 1. Now, if we then stretch in the y direction, this will result in the point 0.01 becoming the point 0.05, and the graph stretches out like that. We should say in each of these examples that in all three of these first examples, that the x-axis or the t-axis is still the asymptote, but in the last example there is a vertical translation which shifts the graph upwards by 25 units, so this y-intercept now becomes, obviously none of this is to scale, 0, 30, and the x-axis moves up to become the line y equals 25, just below like that. So there's our asymptote, and the graph sweeps across like that. Now, of course, time can't be negative in this particular situation, so we may actually not want to include this portion of the graph. We may only want to start the graph at t equals 0. But this is our final sketch here, n equals 25 plus 5e to the 0.4t. Now, just as something can increase very rapidly, it can also decrease very rapidly, and this gives rise to something that we call exponential decay. So here we have an example. A radioactive material decays in such a way that its mass, m, is given by this formula here. The letter t refers to time after the start of the experiment, which is measured in days, and mass is measured in kilograms in this example. So the decay part of this relationship can be seen in the negative here. Remember when we sketched the graph of y equals e to the power of negative x, we saw that it looked like this. So as x increases, y decreases, and we have a decay rather than an increase. So let's have a look at the 4 parts to this question. Part A, what is the mass of material present at the start? This is when time is equal to 0. So m equals 150 e to the power of 0, which is 150 kilograms. Part B, how much material is present after 120 days? Well, let's substitute in 120. So m equals 150 e to the power of negative 0.02 multiplied by 120. Let's work this out. And this is equal to 13.6076, etc., 13.6 kilograms to 3 significant figures. What is the rate of decay? So if we're looking for the rate of decay, we want to differentiate. So we want to find dm by dt. Look back at how we did this previously. So this is going to be 150 multiplied by negative 0.02 e to the negative 0.02t, which simplifies to negative 3e to the negative 0.02t. And it's this negative here in the rate function that shows us that it is a decay or a decrease. Now, what is the rate of decay after 50 days? If t is equal to 50 and we substitute that in, dm by dt is going to equal negative 3e to the negative 0.02 multiplied by 50, which equals negative 1.1036, etc. So negative 1.10 to 3 significant figures. And of course, we need to include a unit with this, which is kilograms per second, or kilograms seconds to the -1. Now, the last part of this asks us to complete another sketch graph of m versus t. Again, we can look at the 3 composite functions which take place here. We have a stretch in the x direction, with a scale factor equal to 50, which is 1 over 0.02. We have a reflection here in the y-axis, and we have, last of all, a stretch here in the y direction or parallel to the y-axis with a scale factor of 150. So again, we can sketch these in 3 different stages and check on our graphical calculator. So in the top right hand corner I have a sketch of m equals e to the t. Let's sketch each stage of the composite combination of transformations. First of all, the stretch in the x direction, scale factor of 50. The x coordinates will multiply by 50. The y coordinates will remain the same. So the graph will simply be a stretched out version of itself. The y-intercept will not change at this stage. The asymptote will not change either. We then have a reflection in the y-axis, which is the next stage here. So the graph simply switches in a mirror image like so. The y-intercept still doesn't change. And in the last stage of the transformation, we then multiply all the y-coordinates by 150. The x-coordinates stay the same, so the graph now looks like this, with a y-intercept of 0, 150. The asymptote remains as the x-axis. And again, doesn't really signify a huge amount for t to be negative here, so I may well exclude this portion of the graph.